Okay, now that we have completed the recap of the concepts from the Introduction to Digital Systems course, let's talk a little bit more about what makes this course, Digital System Design, complicated, and more importantly, what are the kinds of things that we are going to be focusing on as part of this course. We already know that these are our building blocks, right? We have gates, for example, AND gates, OR gates, NOT gates, combinational. We have flip-flops or registers, whatever you want to call them, right, which are sequential elements. Now, for example, I could construct a circuit like this, right? Essentially what the circuit consists of is there is a flip-flop, there is a clock input to it, the output of the flip-flop goes through an XOR gate, and the output of that XOR gate is fed back into the input, right? A perfectly valid circuit by actually sort of stepping through and sort of seeing what happens for different values of x as a function of time, as different clock cycles go through over here, you should be able to also say what the behavior of this particular circuit is going to be, right? And this is fine, this is a perfectly legitimate way of designing a circuit. Or rather, what I would say is that what I am telling you is I am giving you a circuit and then I am saying, okay, I can probably do some analysis and tell you what the circuit is doing, or at least how it is going to behave, right? But that is not really the process by which we go about designing systems. What we want is to sort of go in the other direction. We want a problem description, and from there to be able to build up a circuit that actually has the kind of behavior that we expect. If you look closely at the circuit, you will find that already even just describing what exactly it does is not very easy. So if you start thinking about the reverse problem and saying, okay, what kind of description would have led me to construct a circuit of this sort? Can I give a logical description that would lead me to constructing a circuit like this? It's not that straightforward, right? But that's not necessarily what we care about. We don't particularly care about how do I end up with this circuit. What I do care about is, given a description, what kind of circuit would have that behavior. The first and foremost step towards going in that direction is the use of so-called modules, right? And this is basically the idea of modular design, right? It's a gateway to creating more complex designs. Many of you may be familiar with the idea of Lego, right? Lego, the toy, essentially consists of a set of bricks, very generic bricks, that can then be put together and assembled to create really complex large systems. In some sense, that's precisely what's happening in the context of digital design, right? We have the idea of very basic systems such as gates and registers, and by combining them we can now construct arbitrarily large and complex designs. Now, just like in Lego, if you just took a bunch of bricks and connected them haphazardly, you would get a shape, but it's not clear what it would do, right? Whereas if you wanted, let's say, to build a truck, you need to have something which basically gives you a platform, which allows you to build the axles, it allows you to connect the wheels in a specific location, you can build the cabin of the truck, you need to place the doors and the lights and so on in specific locations, right? Or at least something that looks like that, so that it looks like a realistic truck. In the same way, when you go about building large digital circuits, you don't start by just throwing a bunch of gates and seeing what happens. What you do instead is you actually go in there and say, okay, how do I systematically build up components or smaller modules that can then be assembled together to give a large, complicated design with the desired functionality. So what I'm going to do over here is talk about a few of these modules. Once again, to some extent, this is a recap of things that you would have done in the digital systems course, right? The idea is to sort of go through this and sort of see what are the general concepts that we are bringing in here that will allow us to build larger and more complicated designs. Now, one of the most basic and yet useful modules that we can think of is a so-called multiplexer, usually shortened to the term MUX, right? So a multiplexer typically has these inputs. It has two inputs, A and B over here. It also has one more input, which is usually called the select input, and it has one output, which I am calling Y in this case. I usually also attach these labels 0 and 1 to the different signals that are present over here, so that I can interpret what the MUX is supposed to do. And by looking at this, I can straight away say what this MUX is doing is, whenever the value of S is equal to 0, the value A should get connected to Y, and whenever the value of S is equal to 1, the value B should get connected to Y. Now the first thing you can ask is this a combinational circuit or a sequential circuit? Well, first thing, I have not drawn a clock, so that's a good clue that maybe this is not a sequential circuit. But if you think about it, it is very definitely a combinational circuit, right? What I want over here is, I want immediate response. Anytime I change the value of S, I should see that either A or B immediately gets reflected at the output. So logically, the statement that I have is Y should be equal to A if S is equal to 0, else it should be equal to B, right? When I say else B, what I mean is else Y is equal to B, because after all this is all an assignment that I have out here. So that in some sense is the logical description of what I want from a mux. I can convert that into an equivalent Boolean statement, right? And this is what it looks like. It basically says A and S bar, that is to say S bar will be true when S is false, or when S is equal to 0, S bar will be equal to 1. Now we know that the AND operation is such that if one particular part of it is 1, the other one is what is going to go through to the output, right? If A was 0, the output will be 0, if A was 1, the output will be 1. Great, so this looks like it's doing at least part of what we want. Now if we combine it and say B dot S, right, what that says is whenever S is equal to 1, the value B will come through, and when S is equal to 0, effectively this term drops out of the circuit, right? So what I have done is, because one of these terms has S bar and the other has S, at any given point in time only one of them is going to actually be active, right? And it ensures that this particular equation realizes this functionality that we wanted out here, right? And if we look at it, I can now take this Boolean expression and convert it down to the gate level, right, where what I say is, okay, this is what it looks like. There's an AND gate, there's a S signal that comes in here, this is an inverter to create S bar, and that is another AND gate, and the two of them go through an OR gate to generate Y. All these expressions or diagrams are exactly equivalent, they mean exactly the same thing, right? They are all different ways of representing the same thing. So this is an example of a mux. Now we can go further and we can basically say, what if I have an n to 1 mux, right? So it's usually called an n cross 1 mux, or sometimes an n is to 1 mux, right? 4 is to 1, 8 is to 1, or 8 cross 1, and so on, right? So this is an example of a so-called 4 cross 1 mux, right? It basically says if the input is 0, then the output should be I0. If the input is 1, the output should be I1, right? So basically this expression out here, if the input was 2, right? Now comes the question, okay, how do I represent 2? And the choice I am making here is to say that, okay, this is going to be a binary number, right? And basically I will treat this S1, S0 as 2 bits and say, okay, it is 1, 0 basically corresponds to the value 2. And similarly 1, 1 corresponds to the value 3, at which point I3 comes through to the output. So we have a nice compact mental model of how the 4:1 mux works. How would this actually look at the gate level when it's built, right? This is part of the circuit that could be used over here. Basically what it says is, when should I0 come through to the output? When both S1 is 0 and S0 is 0, right? So S1 is 0 means S0 is 0 means S0 bar will be 1. S1 is 0 means S1 bar will be 1, which means this AND gate has now got activated, and whatever is the value of I0 will come through to this point. Now the other 4 AND gates should be set up in such a way that they are mutually exclusive. At any given point in time, only one of those AND gates should get activated to this point. Then the nice part is, if I just sort of OR everything together, it gives me the output that I want. In practice, this may very well be the way that this is actually getting implemented. There is also another way by which we could do it, which is I could say that I am going to use 2x1 muxes and build up a 4x1 mux by basically cascading 2x1 muxes, right? An example of that would be, I take I0, I1 and feed them into the first mux. Now I apply the signal S1 to select between them. These are mutually exclusive, which means that at any given point in time only one of these two paths is going to be active, right? But the interesting thing is, after that I can then decide based on the value of S0, right? If S0 is equal to 0, I would basically say, okay, let I0 come all the way through to the output. Whereas if S0 is equal to 1, I would then take the other value which is coming from here, presumably I2 or I3, whichever one out because of S1, right, and get that through to the output. Okay. So it is, in other words, possible to create a 4 cross 1 mux by cascading two 2 cross 1 muxes together. There is also the notion of something that we sometimes call a wide mux, right? And the idea of a wide mux is something that's going to be very common as we build larger digital circuits. It's a very simple idea. Basically what it's saying is this is a 2 cross 1 wide mux, right? But I use this notation where I say that basically I0, for example, is an 8-bit value, right? So this slash across the signal with the number 8 written above it or next to it indicates that that particular wire is a bus, right? And what do I mean by a bus? Just a collection of wires, right? So this bus over here basically is an 8-bit wide bus. Similarly, I1 is also an 8-bit wide bus. S on the other hand is a single bit selector, right? What it says is if S is equal to 0, then I0, all 8 bits of I0 together are going to come through to Y. If S is equal to 1, then all the 8 bits of I1 are going to come through to Y. So Y is also an 8-bit value. The interesting thing here is at no point am I going to end up with some bits from I0 and some bits from I1 coming through to Y. Y is never going to be a combination of these two. It's going to be either all of I0 or all of I1 coming through separately, right? In terms of notation, what we will find, and we will be going into this in more detail later as we sort of get more practice with describing this, we tend to use certain kinds of notation. For example, we say that the 8 bits of Y are referred to as Y7, Y6 and so on up to Y0, right? We don't say Y0, Y1 up to Y7. The convention once again is to have the highest numbered bit as the left hand side. Basically it's called the most significant bit, and the lowest numbered bit is the least significant bit. So the convention is to go Y7 down to Y0. In terms of the languages that we will be using for programming, we will usually refer to it as Y of 7:0, right? So you can see that unlike in a C array where you would basically refer to it as something which basically says, you know, I have an array of 10 numbers, the numbers are A of 0, A of 1 up to A of 9, right? I never sort of say A of 9:0 to indicate that it is counting down from 9 to 0. I always have this notion that arrays are things which I start and then move forward in them. Whereas in hardware, we very often come across this idea of most significant bit on the left hand side, least significant bit on the right hand side, and this notation is used for that. Similarly, I1 is an 8-bit value, I0 is an 8-bit value. Once again, MSB to LSB locations are specified in this way. Okay, so muxes are done. Can we build more complicated circuits? Of course the answer is yes. How do we do it, right? Let's assume that A and B are two numbers now, right? But they are 1-bit numbers, which means that they can actually only take on either the value 0 or 1. Now if I tell you that, you know, you have like two 1-digit numbers and you are working in decimal, you would say, okay fine, I have like two 1-digit numbers, each number is between 0 to 9 and you know how to add them, right? So if I have 5 plus 6, for example, I know that if I have 5 plus 3, I know that the answer is 8. If I have 5 plus 6, I know that the answer becomes 11, which goes out of the range of 1 bit, right? So I have some kind of a carryover being generated. All of that is just intuition. Not intuition, it's at least something that you are used to at this point. The same thing can be done in the context of binary as well, right? So I can talk about A plus B, where now this plus is not the OR operation, this is actually the arithmetic plus, right? Potentially confusing, usually clear from context, so please keep that in mind when you look at such expressions. Now if A and B are two numbers, A could be 0, B could be 0, A could be 1, B could be 1. Those are the combinations. Of course, A0, B0, A0, B1, A1, B0, A1, B1. Those are the actual 4 possible different combinations that you have, which basically we can write down as a truth table out here, right? And the interesting thing is that the result A plus B could be either 0, 1 or 2. 2 in binary needs to be represented as 1, 0, which basically corresponds, if you think about it, to a carryover, right? It basically says I can't fit everything within a single bit, I need a carryover over here, which is the 1. Alright, so let's take the output and basically say I'm going to have a 2-bit output rather than a single bit, right? And say, okay, when the input is 0, 0, the output should be 0 on the sum and 0 on the carryover. When it's 0 1 or 1 0, it should be 1 on the sum and 0 on the carry. And finally, when both the inputs are 1, I want 1 0 as the output. That is, I have a carryover, but then the digit that comes in the 1's place becomes a 0. Okay. This particular circuit that I have drawn here is what's called a half adder, right? And if you look at it, now that we have a truth table, we can basically take this and condense it down and say, okay, this corresponds to the Boolean expression A and B, and this corresponds to a Boolean expression A XOR B, right? So now you see the interesting thing. Basically, we took something that was a pure arithmetic operation out here and converted it into a set of Boolean expressions. A full adder takes this one step further. It basically says, when I am actually trying to build larger adder circuits, I will actually have also the potential to get a carry input. Let's say from the 1's place to the 2's place, from the 2's place to the 4's place, from the 4's place to the 8's place, and so on, right? So if I want to handle that, I need to be able to handle a carry in coming in at one point, which means I now have 3 inputs, A, B and C in, which means I have a truth table with 3 inputs or 8 possible combinations. The possible outputs are 0, 1, 2 or 3. There is one particular scenario where the output becomes 3. That's fine, I can still represent all those using 2 bits, right? 0 is 0, 0, 1 is basically a 0 in the carry and a 1 in the sum, 2 is a 1 in the carry and a 0 in the sum, and 3 is 1 in the carry, 1 in the sum, okay? Which means that I can now build up a set of equations corresponding to this as well. Now once I have a adder which is already a full adder, so to say, right, I can now construct a multi-bit adder where I basically take 2 inputs A and B, which are 4 bits each, for example. But now I need to keep in mind that if I add 2 4-bit numbers, the result can be up to 5 bits wide. Why is that? Because with 4 bits, the largest number, ignoring 2's complement and negative numbers and so on, is 1111, which is 15, right? 15 plus 15 is 30. 30 cannot be represented using just 4 bits. I need 5 bits, right? Do I need more than 5 bits? No, I can be sure that the maximum is going to be twice of the largest value, right? And 1 extra bit is enough to account for that doubling. Okay? So I know that 30 is the largest value that I can have, therefore I can have up to 5 bits, but the way to think about that is I actually have 4 bits of the sum and potentially a carry out or an overflow that goes beyond the 4th bit. So I can now think of this as, add these values, I get a 4-bit sum and potentially a 1-bit carry out, or I could think of it as an overflow. And once I have that in mind, I can then construct a circuit straight away from the components that I have built up so far, right? So how did we go with this? We basically started off with gates, from there we went to half adders and full adders, and now we have put those together in order to create an actual 4-bit adder, right? This is what's commonly called the ripple carry adder. You'll probably see, there's a lot of study about different kinds of adder architectures and so on. The ripple carry is not normally considered a very efficient form of adder because it has this problem with a long carry chain. But it turns out that in FPGAs, which we'll talk about later, ripple carry chains are actually extremely optimized and quite powerful. So ripple carry adders are good enough for a lot of purposes, and it turns out that this is how you can build them. So now let's see where we are, right? We have these modules, we have an adder. In the same way as an adder, we could define a subtractor, right? I could basically talk about how I could basically take 2 inputs and basically do B minus A, right? In practice, this doesn't normally happen. What is actually done is we use the trick of 2's complement and basically say that a way of subtracting a number from another is to basically complement it and add, right? So 2's complement has some very nice properties in terms of how you can basically use addition to perform both addition and subtraction. So the hardware is much simpler that way, but for argument's sake, let's assume I have a different module that performs subtraction. Now I might also have something which basically takes 2 8-bit numbers and performs a bitwise AND operation across them, right? Why? Well, there are scenarios where this becomes useful, right? I might basically, for example, from the embedded systems course, you probably know about how we do bit masking, right? We create a mask and we want to mask out and find out what the value of a particular bit is. This is precisely what happens over there, right? A bitwise AND operation. I could do bitwise ORing, once again common in bit masking, right? And of course we have also designed muxes, wide muxes, n cross 1 muxes and so on. Okay, so where does that leave us, right? Do we have anything interesting that we can build so far? Well, let's try and build a large circuit which basically looks like this. It's a big box out here. Inside the box, what do we have? I have an adder, I have a subtractor, I have a n bit AND gate and a n bit OR gate. Now I take these two 8-bit values A and B and basically just connect them up to all of those inputs. So A is basically wired up to all 4 of these, so is B, right? So at any given point in time these connections are always there, right? This is just hardware. I have literally like connected them up together. Any change in A or B will immediately reflect at the outputs of all 4 of these, right? They are not going to wait and say, okay, which one are you actually trying to do? All 4 of them will respond immediately. That's the nature of combinational circuits, okay? Now that I have done this, I don't want to do all 4 operations all the time, but what I am saying is, a simple way of doing this is just perform all the 4 operations. After that, put a multiplexer. What does a multiplexer do? It basically takes an input, which I am calling op over here, right, for reasons that will become clear later. And the op basically is a 2-bit input. Why? Because this is a 4 cross 1 mux. It basically selects one out of these 4 inputs and brings it through to the output, okay. Now think about what we have done here. We have basically had something which takes in 2 inputs. It performs different kinds of arithmetic or Boolean or logical operations and selects one of them through to the output, right. The term that's normally used for this is the ALU, the Arithmetic and Logic Unit. This is pretty much how the ALU of a CPU, a processor, looks like, right. Of course it's a simplification. In practice you will need to do some additional steps over here, primarily to get speed, not for functionality. The functionality is already set over here, right. Functionally this behaves like what an ALU needs to do, right. But there are certain optimizations that we will probably do, because for reasons that will become clear later, right, there are aspects of the hardware implementation that actually affect the timing, the speed with which a particular circuit can work, okay. But this is pretty much what an ALU looks like. Okay, now let's keep that to the side and say, okay, let's go one step further and say, let's look at registers for a bit, right. Look at this particular architecture. What it says is, I have a flip-flop. The output of that flip-flop goes in through a mux and comes back, okay. And there is a signal called CE out here, which basically allows me to decide whether this output is the one that's coming back into the input, or this input from here, A, is the one that's going to come into D, right. So if you think about it, what it says is, if I keep CE equal to 0, this flip-flop is just going to retain its last state. It will never change its value, right, no matter how many times the clock edge changes. So that's interesting, because basically what I can do is I can just connect up the clock to a large number of registers and then use the CE to selectively control which of the registers get updated. I don't need to turn off the clock. Yes, turning off the clock could also have achieved this. Turning off the clock is a bad idea for other reasons, which we will get to later, okay. So the CE signal is sometimes called the chip enable or the clock enable. It's an enable pin essentially, right, which basically allows us to choose between either an external value or the feedback value to be coming into the register for the next cycle, okay. So far looks good. I can now take several of these registers together, just physically place them near each other if necessary, and then say, okay, I have a 4-bit A. I take those 4 bits and basically split them out and connect each one to a mux like this, and then after that into a register, right. So basically this is 4 copies of this feedback register out here with the muxes and so on. The interesting thing is, I put a common clock enable to all 4 of them. What that means is, whenever this enable pin becomes high, all 4 bits get copied over and stored inside this register. Whenever the enable pin is low, all 4 bits of the register remain unchanged from what they were previously. So in other words, I am now able to move data around in chunks of 4 bits, or I could very well easily make this 8 bits or 32 bits or however big I wanted the register to be. This is just like the wide mux that we talked about earlier, right? I now have a wide register. Okay, so I can basically do a parallel update of up to 4 registers, of these 4 registers over here. Either all of them get updated values from here, or all of them just retain their last value from here. Okay. Now I can go one step further with that and say, okay, now I have these n-bit registers, wide registers, and I have a wide mux. I'm going to take the outputs of many such wide registers and use, well, in this case 4 of them, and put a 2-bit read select and say, depending on the value that I want over here, any one of these 4 registers needs to come through to the output. Okay, so this is basically a 4 cross 1 read select that I have, right? Okay, so what it means is if I had values stored in these 4 registers, I could basically decide that which one I am going to read over here. Now, can I also selectively update or change the values in these registers? Yes, the answer is fairly straightforward for that. All I need is, take this input A and connect it to all 4 of them simultaneously, but enable only one of them. Which one should I enable? I use another write select signal and say, based on the write select signal, either 0 or 1 or 2 or 3, these bits are going to become equal to 1. And they are mutually exclusive. At any point, only one of them is going to be equal to 1. Whichever one becomes 1, that's the value into which this A is going to get written. The other 3 are going to remain unchanged, right? So what have we achieved over here? If I look at this whole block, now suddenly I have the ability to read out any one of these registers or write into any one of the registers. By using write select and read select, I can choose which one of these registers I want to go into, right? Hopefully by this point, this is reminding you of the idea of registers in, let's say, an ARM processor, right? I can have many registers out here. I can choose one of those registers and write a value into it. I can choose one of those registers and read a value out of it. And all this can be done by just changing some select signals that I have out here, right? I know how to do arithmetic operations. I know how to read data from registers. What I can do is put all of this together and say, take my ALU, take my register file, have some way by which I, rather than reading one value, let's say that I read 2 different values by having read select 1 and read select 2, right? I give the register select from somewhere. What is that somewhere? We'll get to that in a moment. I do my operation select also from the same place where I did my register select. The output which comes from the ALU, I send it to the register file, and the write select also comes from this pink box that I have drawn over here, right? Now that pink box essentially is, for all practical purposes, an instruction, right? It tells you what operation to perform, which registers to take as input, and which register to write the output to. And by further having a sequence of such registers or memory locations out here with different values stored, right, we have created a set of instructions which is the program memory of a processor. And if you think about it, all that I now need to do is add a couple of more different types of instructions, the ability to load or store data from some external memory into this register file, right, and also the ability to jump from one place to another within this set of instructions by basically changing the address that I pass into this memory, right. Once I have done that, I have ALU operations, load store operations, branch operations. I have a processor, a CPU as we normally say. The RISC V processor is very nice in some ways because it sort of simplifies it to the point, simplifies the entire instruction set to the point where you can literally see how all this is happening, right. So it's, the point I wanted to make over here is that designing something of that sort and that level of complexity is not very hard, right. What gets hard is when you actually want to get high performance out of it, when you actually want it to run fast, when you want it to do things that are not, going to be basically slow and cumbersome and stage by stage, right. That definitely is non-trivial. That is where most of the sort of innovations in processor architecture design happen, right, and continue to happen these days. But the very core, the basic idea of what a processor is actually very simple and easy to understand.